number 2, no? Assignment B. Okay? Then we will have our quiz. Again, the same ang atong process sa quiz, no? Katong dunay multiple choice, dunay short answer quiz. Doon na pud in the kuan sa ato ang multiple choice, doon na tay mga problem solving, no? And you are going to choose only the answer, no? Of course, you are going to compute that, no? Okay? Ang atong assignment is purely analytical, no? So mag-solve kita sa atong assignment. Okay? So we start now. Uh, okay, we will bypass the PowerPoint because I will be just uploading this one in our course module. Okay. Okay, so start.
Number 4. If Kc for the reaction shown below is 9.6 at 300 Celsius, what is the value of Kp at this temperature? Now, this is a formula that we could use to go from Kp to Kc or vice versa. But let's talk about how to get that formula. So let's say we have a generic reaction, A plus B turns into C plus D. And we're going to have our generic coefficients, J, K, L, and M. Let's write the equilibrium partial pressure expression for this reaction. So Kp is going to be the partial pressure of the products, so the partial pressure of C, and that's going to be raised to the L power, times the partial pressure of D raised to the M power, and that's going to be divided by the partial pressure of A raised to the J power, and then times the partial pressure of B raised to the K power. Now, based on the ideal gas law equation, we know that PV is equal to nRT. So if we divide both sides by the volume V, we get P is equal to nRT over V. But instead of writing it that way, we can write it like this, N over V. Because concentration is moles divided by volume. So we can replace N over V with C. So we get the pressure is equal to the concentration times RT. So I'm just going to rewrite that here. So now what we're going to do is we're going to replace P with CRT in this expression. So the partial pressure of C, we can replace that with the concentration of C times RT, and it's going to be raised to the same exponent, L. So let's do the same for the rest. So the partial pressure of D is going to be the concentration of D times RT. The partial pressure of A is going to be the concentration of A times RT. And the same is true for the partial pressure of B. That's going to be the concentration of B times RT. And let's put the exponents, M, J, and K. So now what we're going to do at this point is we're going to separate the concentration from RT. The concentration of C, we can simply put it in brackets. It will be just C. But let me rewrite this over here. So keep in mind, this whole thing is still equal to Kp. We can delete this as well. Actually, let's keep that for now. So this is going to be the concentration of C, and then times RT. This is going to be the concentration of D times RT. Now keep in mind, this is raised to the L. So this is the concentration of C raised to the L and the concentration of RT raised to the L. And then this is the concentration of D raised to the M times the concentration of RT raised to the M. You have to distribute the M to both D and RT. Now the concentration of A, we can simply just put that in brackets as well, and then times RT, and those two will be raised to the J power. And then we have the concentration of B, which is raised to the K power, times RT, which is also raised to the K power. And this is still equal to Kp. Now what I'm going to do is I'm going to break this fraction into two smaller fractions. In one fraction, I'm going to collect all of the concentration terms, and then in the other fraction, all of the RT terms. So here we have the concentration of C times the concentration of D divided by the concentration of A and B. And then let's put the exponent. So this is L, M, J, and K. Now, let's multiply these two. If we were to multiply two terms with the same base, we can add the exponents. X squared times x cubed. This is going to be x raised to the 2 plus 3, which is x to the 5th power. So if we multiply these two, we can add the exponents L and M together. So this is going to be times. So we're going to have RT raised to the L plus M. And then we could do the same thing with those two. We can multiply them, and then we can add these two exponents together, J and K. So we're going to have RT raised to the J plus K. So all of this is still equal to Kp. So we could say that Kp is equal. Now this is the equilibrium expression for Kc, products over reactants, but in terms of concentration. So we can replace this whole thing with Kc. So we have Kp equal Kc. Now that part, what happens when we divide by, if we divide two common bases? Let's say if we have x to the 7 over x to the 4th. We can write that as a single x variable by subtracting the exponents. 7 minus 4 is 3. So we can write this as a single RT value by subtracting L plus M and J plus K. So we're going to get times RT raised to the L plus M we can write that as a single x variable by subtracting the exponents. 7 minus 4 is 3. So we can write this as a single at this temperature. Now this is a formula that we could use to go, it will be just two. Let's say if we have x to the 7 over x to the 4th. We can write that as a single x variable by subtracting the exponents. 7 minus 4 is 3. So we can write this as a single RT value by subtracting L plus M and J plus K. So we're going to get times RT raised to the L plus M minus J plus K. And this is in parentheses. Now, we can define delta N as being the sum of the coefficient of the products minus the sum of the coefficients of the reactants. So J and K represents the coefficients of the reactants. L and M represents the coefficients of the products. So delta N is basically the sum of the coefficients of the products minus reactants. So now we have our equation that relates Kp and Kc. So this is the equation that you want to write down in your notes. Kp is equal to Kc times RT delta N. And remember, delta N is the sum of the coefficient of the products. Let's say Cp for coefficient of the products minus the sum of the coefficient of the reactants. Or you can write it this way if you want. The important thing is that you know how to apply it in a problem. So now, in part A, we're given Kc, and we want to find the value of Kp. So Kp is going to equal Kc, which is 9.60, times R. Now there's two R values. There's the R value that is associated with energy, 8.3145, the units of which are joules per mole per Kelvin. And then there's this R value, 0.08206, liters times ATM divided by moles times Kelvin. Now, Kp, which is described in terms of partial pressure, it's usually in units of ATM. Therefore, you want to use this R value, which contains the unit ATM. So it's going to be 0.08206, and the temperature has to be in Kelvin. So 300 Celsius, to convert that to Kelvin, we need to add 273 to it. So it's going to be times 573 Kelvin, and then raised to the delta N. So let's calculate delta N for this reaction. So delta N is going to be the coefficient of the products, which is 2, minus the sum of the coefficients for the reactants. So that's 1 plus 3. So delta N is 2 minus 4, which is negative 2. So we're going to raise this to the negative 2 power. And that's going to give us Kp. So let's go ahead and plug that in. So this is going to be 4.34 times 10 to the negative 3. So that's the value of Kp for part A. Now let's calculate the value of Kc. So how can we do that? To get Kc, Kc is going to be Kp divided by RT raised to the delta N. So that's the formula we need to get Kc. In part B, we're told that the value of Kp is 1.45 times 10 to the negative 3. And we're given the temperature as well. The temperature this time is 500 Celsius. R is still going to be the same. It's 0.08206. And the temperature is going to be 500 Celsius plus 273, which is 773 Kelvin. Delta N is not going to change because the coefficients for this reaction remain the same. So delta N is still negative 2. Thus, Kc for this reaction is 5.83. So now you know how to calculate Kp given Kc, and you also know how to calculate Kc given Kp. Number 5. Given the value of K for the reaction shown below, what is the value of K for the adjusted reaction? Or more specifically, K prime. So notice that we doubled the coefficients of the first reaction. How is that going to affect the value of K? When you double the reaction, the new value of K is going to be the square of the original value of K. So K prime is going to be K squared. Thus, that's going to be 100 squared, which is 10,000. So that's going to be the new value of K for this adjusted reaction. Now, if you're wondering why K prime is equal to K squared, here's the reason. So let's get the equilibrium expression for the adjusted reaction. So that's associated with K prime, and it's going to be products over reactants. So we have NO2 on top, NO and O2 on the bottom. And then the coefficients become exponents. So what we're going to do is we're going to factor out a 2 from every exponent. If we do that, if we factor out a 2 from 4, this becomes 2. This also becomes 2. And if we factor out 2 from 2, that becomes 1. Now this whole thing is going to be raised to the second power since we factored out a 2. What is the value of Kp Kc square root Now, how can we show that this is 1 over k? Let's multiply this part of the fraction by NO squared. That is the bottom of this fraction highlighted in blue. And we're going to multiply the top of that fraction by NO squared. So if you multiply a fraction by NO squared over NO squared, you're multiplying it by 1. You're not changing the value of that fraction. Here, NO squared will cancel. And so what we're going to have left over is K prime is equal to 1, and then that's this line in white, divided by NO squared. I'm going to draw the fraction line that's highlighted in blue, which is this line, over NO squared times O2. Now, this expression here, what is the value of Kp at this temperature? Fraction line that's highlighted in blue, which is this line, over NO squared times O2. Now, this expression here, where NO squared is on top, and on the bottom we have, NO2 squared is on top, and on the bottom we have NO squared times O2, the reactant side. This is the equilibrium expression for the original K. So we can replace this with K. So that's how we could show that K prime is 1 over K when you reverse the reaction. So now that we have the value for K prime for this one, let's try a new one. So let's say we have this reaction, but the coefficients are 6, 6, and 3. What's the K value for this reaction? So if we compare it to the original expression, the reaction has been reversed. So we know K prime is going to be 1 over K. And if we compare the coefficients, we've multiplied the reaction by 3. Whatever you multiply the reaction by, you need to raise K to that exponent. Since we multiplied it by 3, we're going to raise it to the third power. So K prime is going to be 1 over K cubed. So that's 1 over 100 to the third power, which is 100 times 100 times 100. That's 1 with 6 zeros. So that's a million. A million is 1 times 10 to the 6, since we have 6 zeros. If we move 10 to the 6 to the top, go to the concentration times RT. That the reactant side. This is the equilibrium expression is liters. K when the reaction is adjusted, which is 100 times 100 times 100 million is 1 times 10 to the 6, since we have 6 zeros. If we move 10 to the 6 to the top, the exponent changes from positive 6 to negative 6. So this becomes 1 times 10 to negative 6. So that's the new K value that corresponds to this reaction. So now you know how to calculate K when the reaction is adjusted. Either you reverse it, multiply by 2, or multiply by half, and so forth. 20 moles of NaCl is placed inside an empty 4-liter container. At equilibrium, 8 moles of Cl2 was found to be in the container. Calculate the value of Kc for this reaction. In order to calculate Kc, we need to find the equilibrium concentrations for every species in this reactant. We don't have that. What we need to do is write an ice table. So at the beginning, the initial value of NaCl can be calculated. Notice that we placed 20 moles in a 4-liter container. So to calculate the concentration, it's moles divided by liters. So we have 20 moles of solute divided by 4 liters. So that's going to be 5 moles per liter. That's the initial concentration of NaCl. Now the container is empty, so we don't have anything for NO or Cl2. So we're going to place a 0 there. Now, because the products are equal to 0, the reaction has to shift towards the right. It cannot shift to the left. And so Cl2 is going to increase by some amount 1x. Now, notice the molar ratio between NO and Cl2. It's 2 to 1. So if Cl2 increases by x, NO is going to increase by 2x. And NOCl is going to decrease by 2x. As the reaction shifts to the right, the products will increase in value, but the reactants will decrease in value. So if we add the first two rows, this is going to be x, 2x, and 5 minus 2x. Now the concentration of Cl2 at equilibrium is x. And we also know that at equilibrium, 8 moles of Cl2 was found to be in the container. So the concentration of Cl2 at equilibrium is going to be 8 moles divided by the 4-liter container. So it's 2 moles per liter. So now we know the value of x. X is equal to 2m because they're both equal to Cl2. So now we can find the equilibrium concentrations for everything else. For NO, it's equal to 2x. And since x is 2, that's going to be 2 times 2. So NO is equal to 4m. Now we can also calculate the equilibrium concentration for NOCl, which is equal to 5 minus 2x. So that's going to be 5 minus 2 times 2. So that's 5 minus 4. So it's 1 mole per liter at equilibrium. So now that we have the equilibrium concentrations for every reactant and product in this example, we can now write the expression for Kc. So products over reactants, on the product side we have NO and Cl2, and for the reactant side we only have NOCl. The coefficient for NO is 2, the coefficient for Cl2 is 1, and for NOCl that's 2. So now let's plug in the values. So for NO, that's going to be 4. For Cl2, it's 2. And for NOCl, it's 1. So 4 squared is 16, and 1 squared is 1. 16 times 2 is 32. So Kc in this example is 32. And that's the answer. Carbon monoxide reacts with oxygen gas to produce carbon dioxide. At equilibrium, the concentrations of O2 and CO2 are 0.10 and 0.75 moles per liter, respectively. So we're given Kc. What is the concentration of CO at equilibrium? The first thing we need to do is write a balanced chemical equation. So we have carbon monoxide reacting with oxygen gas, and it's going to produce carbon dioxide. So to balance it, we just need a 2 in front of CO and CO2. And so we have Kc for this reaction. 10 to the third is 1,000, so this is going to be 4,000. Now, we have the concentrations of O2 and CO2 at equilibrium, so we don't need an ice table to find the equilibrium concentration of CO. Let's write the expression for Kc. So it's products over reactants. On the product side, we have CO2, and on the reactant side, we have CO and O2. The coefficient in front of CO2 is a 2, so we need to put that here. And for CO, it's also a 2, and it's a 1 for O2. Now, Kc is 4,000. The equilibrium concentration of CO2 is 0.75. And the value for CO is what we're looking for. So let's call that X. And the concentration for O2 is 0.10. So let's cross multiply. So first on the left side, we're going to have 1 times 0.75 squared. which is 0.5625. And on the other side, we're going to have 4,000 times zero point 0.1, which is 400, multiplied by x squared. Now we need to divide both sides by 400. So 0.5625 divided by 400, that's 1.40625 times 10 to the minus 3. So that's equal to x squared. So now we got to take the square root of both sides. And so x is 0.0375. So that's the concentration of carbon monoxide at equilibrium. Number 8. At a certain temperature, ammonia partially decomposes into nitrogen gas and hydrogen gas. Ammonia was added to an empty container until the partial pressure of NH3 reached 0.85 atm. At equilibrium, the partial pressure of H2 was found to be 0.45 atm. What is the partial pressure of NH3 at equilibrium? Well, first we need to write a reaction. So ammonia is decomposing into nitrogen gas and hydrogen gas. And we've seen this reaction plenty of times, so we know how to balance it. Now, we have partial pressures at equilibrium and initially, before the reaction begins. The 0.85 atm, that's the initial partial pressure of NH3. And then we have the partial pressure of H2 at equilibrium. Whenever you have information at equilibrium and before the reaction begins, you need to write out an ICE table. Initial, change, equilibrium. So initially, the partial pressure of NH3 is 0.85. We don't have anything else in that container, so the partial pressure of the products is 0. Now, our next step is to determine what direction the reaction is going to go. Is it going to go to the right or to the left? Now, anytime any one of the products is 0, the reaction has no choice but to go to the right. Because if you don't have any products, it cannot go to the left. Otherwise, these will become negative. But since we don't have any nitrogen or hydrogen gas, they can't react together to form ammonia. So the reaction has to go to the right. As the reaction goes to the right, we know that the products will increase in value, the reactants will decrease in value. So this is going to be positive 1x because it's a product, it's going to increase. And this is going to be positive 3x. Let me write that better. The 1 to 3 ratio is based on the molar ratio that we see here. As the reaction shifts to the right, the reactants are going to decrease in value. So we're going to have a negative sign for the change. This is going to be negative 2x. So we have negative 2x, 1x, 3x, based on a molar ratio of 2:1:3. Now let's add the first two rows. So at equilibrium, the partial pressure of NH3 is going to be 0.85 minus 2x. For N2, it's going to be x. For H2, it's going to be 3x. Now that we've completed the ICE table, what should we do next? Now looking at the problem, we're told that at equilibrium, the partial pressure of H2 was found to be 0.45 atm. So we can write that. At equilibrium, we also know that the partial pressure of H2 is equal to 3x. Therefore, we could set 0.45 ATM equal to 3x. And that will help us to solve for x. So let's divide both sides by 3. So x is going to be 0.45 divided by 3, which is 0.15. So that's the value of x. Now that we have that, we can calculate the equilibrium partial pressure of any one of the reactants or products. So our goal is to calculate the equilibrium partial pressure of NH3. So that's going to be 0.85 minus 2x. So let's replace x with 0.15. 0.85 times 2 times 0.15, that's 0.55. My handwriting is terrible today. So this is the final answer for this problem. That's the partial pressure of NH3 at equilibrium. If we want to find the equilibrium partial pressure of N2, it's simply x, which is 0.15. And if we want to, we can calculate Kp for this entire process. So Kp is going to be H2 raised to the third power times N2 raised to the first power divided by NH3 to the second power. It's products over reactants. So we know the equilibrium partial pressure. Actually, I wrote this wrong. This should be the partial pressure of H2 raised to the third power times the partial pressure of N2 to the first power divided by the partial pressure of NH3 to the second power. So the partial pressure of H2, that's 0.45. For N2, it's simply X, which is 0.15. And for NH3, we calculate it to be 0.55 based on that expression, and we need to square it. So Kp is going to be 0.0452. So that is the equilibrium partial pressure constant, if we want to find it. In this video, we're going to talk about how to calculate the KSB value given the molar solubility. So in this problem, the molar solubility of nickel carbonate is 3.74 times 10 to the negative 4 moles per liter. Calculate the KSP value, also known as the solubility product constant for nickel carbonate. Now, the first thing we need to do is write the chemical reaction that's associated with it. Solid nickel carbonate is going to dissociate into the nickel ion and the carbonate ion. So this reaction is in equilibrium. Now, what's important though is the molar ratio. This number that you see here, the molar solubility of nickel carbonate, that is the concentration of nickel carbonate that is actually dissolved in a solution. So that's the amount that is in the aqueous phase. Now, because the molar ratio is 1 to 1, the concentration of nickel and carbonate is also equal to the molar solubility, which is basically that value. Now let's write the KSP expression for this reaction. To write the equilibrium expression for any K value, it's equal to the products divided by the reactants. Now the products are nickel plus 2 and carbonate. Both of these are in the aqueous phase, and the reactant is solid nickel carbonate. Now keep in mind, solids and liquids are not included in the equilibrium expression, so we're not going to include this. So in this example, we just got to plug in the concentrations of nickel and carbonate, which they're the same as this number. They're all equal to 3.7 times 10 to the negative 4. So nickel is going to be the same number, and carbonate is also equal to the same value. So for this problem, it's 3.74 times 10 to the negative 4 squared. And so the KSB for nickel carbonate is 1.4 times 10 to the minus 7. And therefore, this is the answer. Now, let's work on number 2. The molar solubility of calcium hydroxide is 6.875 times 10 to the negative 3. Calculate the KSP value for calcium hydroxide. So first, let's write the dissociation reaction. Solid calcium hydroxide dissociates into calcium and 2 hydroxide ions. And so these are in the aqueous phase. Now pay attention to the molar ratio. So we have a 1 to 1 to 2 molar ratio. So with this reaction, go ahead and calculate the KSP value for this substance. Now let's calculate the concentrations of everything. The concentration of calcium hydroxide in the aqueous phase is given to us. That's the molar solubility. That's 6.875 times 10 to the minus 3. Now the concentration of calcium, notice that these two are in a 1-to-1 ratio. So therefore they have the same concentration. Now the concentration of hydroxide is going to be twice the concentration of this value, or twice the molar solubility, because there's a 2 here. So for those of you who want to show your work, here's what you can do. So starting with calcium hydroxide, the molar concentration is 6.875 moles of CaOH2 per liter. So you can start with that. And then use the molar ratio. The molar ratio is 1 to 2. So for every 1 mole of calcium hydroxide that dissolves, you could say that 2 moles of hydroxide ions are produced. And so you can cancel these units, and now you have the concentration of hydroxide in moles per liter. So it's 6.875 times 10 to the minus 3 multiplied by 2. And so the concentration of hydroxide is 0.01375. So now that we have the equilibrium concentrations of calcium and hydroxide, we can now calculate the KSP value for it. And so KSP, based on this reaction, is going to be equal to the calcium ion concentration multiplied by the hydroxide ion concentration, but that's going to be raised to the second power. Keep in mind the coefficients turn into the exponents in the equilibrium expression. So now we just got to plug in the numbers that we have. So the concentration for calcium is 6.875 times 10 to the minus 3. And for hydroxide, it's 0.01375. 0.375, and we need to square it. And so this is equal to 1.3 times 10 to the negative 6. So that is the KSB value for calcium hydroxide. So now you know how to calculate the KSB value given the molar solubility. Number 3, the solubility of calcium phosphate is 5.1 times 10 to the negative 5 grams per liter. Calculate the KSB value for calcium phosphate. So like before, let's start out with a reaction. So we have solid calcium phosphate, and it's going to ionize into the calcium plus 2 ion, which is in the aqueous phase, and also the phosphate ion. Now we need to balance the reaction. So notice that we have a subscript of 3 for calcium, and a subscript for phosphate is a 2. So now it's balanced. And we're given the molar solubility in grams per liter, as opposed to moles per liter. So the first thing we need to do is calculate the molar solubility in moles per liter. So let's start out with this. We need to find the molar mass of calcium phosphate. So let's go ahead and calculate it. The atomic mass of calcium is 40.08, and there's 3 of them in this formula unit. And then we have 2 phosphorus atoms, each with an atomic mass of 30.97, and there's 8 oxygen atoms. So 3 times 40.08 plus 2 times 30.97 plus 8 times 16, that's equal to a molar mass of 310.18 grams per mole. So we can say that there's 310.18 grams of calcium phosphate per 1 mole of calcium phosphate. So these units will cancel. And so it's going to be 5.1 times 10 to the minus 5 divided by the molar mass, which is 310.18. And so this is going to be 1.644 times 10 to the negative 7 moles per liter. So that's the molar solubility. That's the first thing we need to do before we calculate the KSB. Now keep in mind, this molar solubility represents the concentration of calcium phosphate that's dissolved in the solution. So now let's calculate the concentration of the calcium plus 2 ion. So notice that it's 3 times this particular value. So it's going to be 3 times 1.644 times 10 to the minus 7. And so that's going to be 4.932 times 10 to the minus 7 moles per liter, or molarity. Now the phosphate ion concentration is simply twice the value. And keep in mind, if you want to show your work, you can write it like this. So you need to write that there's 2 moles of phosphate ions per 1 mole of calcium phosphate. And so that's why you need to multiply it by 2. But for those of you who don't need to show your work for some reason, you could just multiply the molar solubility by 2, and then you'll get the phosphate ion concentration. So this is going to be 3.288 times 10 to the minus 7. So now that we have the calcium and the phosphate ion concentrations at equilibrium, we can now calculate the KSP value. Now granted, the solubility that they give you is always the solubility at equilibrium. It's not the initial value. We don't need an ICE table for this problem. So the KSP value is going to be the calcium plus 2 ion concentration raised to the third power, since we have a coefficient of 3, and then times the phosphate ion concentration raised to the second power. So the concentration of calcium, that's 4.932 times 10 to the negative 7. And for phosphate, it's 3.288 times 10 to the negative 7. And don't forget to raise this to the third power and that to the second power. So go ahead and type in what you see in the calculator. So this is equal to 1.3 times 10 raised to the negative 32. So this is the KSP value for calcium phosphate. That's the answer. Number 4. The solubility of the barium plus 2 ion is 2.667 times 10 to the negative 8 moles per liter in a saturated solution of barium phosphate. Calculate the KSP value for barium phosphate. So first, let's write the dissolution reaction. Solid barium phosphate is going to ionize and form the barium plus 2 ion and also the phosphate ion. And looking at the subscripts, it's 3 and 2. So to balance it, we're going to use a 1 on the left, a 3 in front of barium, and a 2 in front of the phosphate ion. Now we need to calculate the equilibrium concentrations of these two ions. We already have barium plus 2, which is good. The concentration for that is 2.667 times 10 to the minus 8. And that's in a saturated solution, so that's the equilibrium concentration. So what we need to do is take this value and convert it to the concentration of phosphate. And we can use the balanced chemical equation to do that. So let's start with 2.667 times 10 to the minus 8 moles of Ba plus 2 per liter. And the molar ratio is 3 to 2. So for every 3 moles of barium that dissolves, 2 moles of phosphate will dissolve along with it. So we could cancel these two units. So it's going to be 2.667 times 10 to the minus 8 multiplied by 2 divided by 3. And so the phosphate ion concentration in this problem is 1.778 times 10 raised to negative 8. Now, let's calculate the KSP. So let's write the equilibrium expression. It's going to equal the barium plus 2 concentration times the phosphate concentration. And we need to raise this to the third power and the phosphate concentration to the second power. So it's going to be 2.667 times 10 to the minus 8 raised to the third power, and then 1.778 times 10 to the minus 8 raised to the second power. So the answer that I got for this problem is 5.997, which is basically 6 times 10 to the negative 39. So that's the KSP value for barium phosphate in this problem. And so this is the answer. Now let's work on a different type of problem. So we have the KSP value for AgBr. What is the molar solubility of silver bromide? Now the first thing that we need to do is we need to write a balanced chemical equation. So we got to write the dissolution reaction for AgBr. So if you were to put solid silver bromide in water, some of it will dissociate into silver cations and bromide anions. Now let's make an ice table. Initially, the concentration of Ag and Br will be 0. As a result, the reaction has to shift to the right. So therefore, the products will increase by X. The molar ratio is 1 to 1. Now, to write the equilibrium expression for this reaction, it's going to be products divided by the reactants. So the products are Ag plus and Br minus. The reactant is AgBr. However, you cannot include any liquids or solids in the equilibrium expression. So this is the KSP expression for this example. Now, KSP for AgBr is 5 times 10 to the minus 13. The concentration of Ag plus is X, and for bromide it's X as well. So X times X is X squared. Now let's take the square root of both sides. So X is equal to 7.07 times 10 to the negative 7 moles per liter. Notice that X represents the concentration of Ag plus and Br minus. Now notice that everything is in a 1-to-1 ratio. So therefore, the concentration of silver bromide that is dissolved in a solution, some of it may be in a solid phase, but the amount that's dissolved in the solution is equal to the concentration of Ag plus and Br minus due to the 1-to-1 molar ratio. So X is also equal to the concentration of the dissolved silver bromide in a solution. So anytime you want to find or calculate the molar solubility of the solid product, the portion that's dissolved in a solution, all you need to do is calculate X. X represents the molar solubility of the substance. And so this is the answer, 7.07 times 10 to the minus 7 moles per liter. For the sake of practice, let's try another one. You can work on this example if you want to. So calculate the molar solubility of lead iodide, or lead 2 iodide. So all we need to do is calculate the value of X. That's going to be the concentration or the solubility of lead iodide that's actually dissolved in a solution. So let's start with the substance in its solid form. And then it's going to dissociate into Pb plus 2 and also iodide. Now we need to balance the reaction. So this is going to be 1 and this is going to be 2. Now let's make an ice table. So this is going to be 0 and 0. Now this is going to increase by 1x and this is going to increase by 2x based on the molar ratio that you see there. So now let's write the KSP expression for this reaction. So it's going to be Pb plus 2 and then times the concentration of iodide. Now the coefficients will turn into the exponents in the equilibrium expression. Now, Ksp for lead 2 iodide is 1.4 times 10 to the negative 8, and lead plus 2 is equal to X, and iodide is equal to 2X. 2X times 2X is 4X squared, and X times 4X squared is 4X cubed. So 1.4 times 10 to the negative 8 is equal to 4X cubed. And keep in mind, our goal is simply to calculate the value of X. So let me rewrite this on top. So at this point, it's all algebra. So what I'm going to do is I'm going to divide both sides by 4 initially. 1.4 times 10 to the negative 8 divided by 4, that's 3.5 times 10 to the negative 9, and that's equal to X cubed. Now the next thing that you want to do is you want to raise both sides to the 1/3 power based on the number you see here. So raise it to the reciprocal of that value. When you raise one exponent to another, you need to multiply. 3 times 1/3, 3 over 3, that's 1. The 3's cancel. So you get x to the first power is simply x. So it's 3.5 times 10 to the negative 9 raised to the 1/3, or you could take the cube root of it. And so x is 1.52 times 10 to the minus 3 moles per liter, or molarity, and that's the molar solubility of lead 2 iodide. You just got to calculate the value of X. The Ksp value for silver phosphate is 1.8 times 10 raised to the negative 18. Calculate the molar solubility of Ag3PO4. So this is similar to the first two problems. Go ahead and try this. So let's begin with the reaction. So we have Ag3PO4 in the solid phase. And then it's going to dissociate into Ag plus, which is in the aqueous phase, and also phosphate, which is also in the aqueous phase. Now let's go ahead and balance the reaction. So notice that the subscript is 3. We're going to put a 3 in front of Ag plus and a 1 in front of PO4. Now let's make an ice table. So this is going to be 0, 0, plus 3x plus x, and then 3x and x. So the Ksp expression is going to be Ag plus times phosphate. And then we need to raise this to the third power and this to the first power. Now Ag is equal to 3x, and that's raised to the third power. Phosphate is equal to x. 3 to the third power is 27. So this is 27x cubed times x. And so this is 27x to the fourth. Now I'm going to show you a shortcut method that can help you to get this expression. The fact that Ksp is equal to 27x to the fourth. And then we'll come back to this problem. Now let's start with our first example, which was AgBr. In this substance, notice that the subscripts is 1 and 1. So to calculate the Ksp, for Ag it's going to be 1x raised to the first power, and for Br, 1x raised to the first power. So you get this expression. The Ksp is equal to x squared. And if you need to calculate the molar solubility, just simply calculate x. Now for the second example, it was PbI2, or PB1I2. So to calculate the KSP expression for PB, it's going to be 1x raised to the first power. For I2, 2x raised to the second power. And this gave us this expression. KSP is equal to 4x cubed. So now for our third example, this works if you're not dealing with the common ion problems, by the way. If you have a common ion problem, which I'll cover that in another video, you need to actually write out the ICE table. But for a problem like this, if you're given a KSP value and you want to calculate the molar solubility and there's nothing else given to you, then you could use this technique. So I just want to highlight that fact. So for this example, we had Ag3PO4. The subscript for PO4 is a 1 because nothing was there. So the KSP is going to be, for Ag, it's going to be 3x raised to the third power, and for phosphate, 1x raised to the first power. And so this is going to be 27x cubed multiplied by x. And so that's how we got the expression KSP is 27x to the fourth. So now let's go ahead and finish this problem. So the KSP for silver phosphate is 1.8 times 10 raised to the negative 18. And that's equal to 27x to the fourth power. Now the first thing you want to do is divide by the coefficient 27. That's step one. So if you divide it by 27, this is going to be 6.67 times 10 to the negative 20. And that's equal to x to the fourth. Now last time, we raised everything to the 1/3. This time, because there's a 4, you want to raise everything to the 1/4 power, because 4 times the 1/4 is 1. So you want to take the 4th root of 6.67 times 10 to the negative 20. And so the molar solubility is 1.607 times 10 to the negative 5. You can write molarity, or you can say moles per liter. So that's the molar solubility of silver phosphate. Now let's move on to part B. What is the concentration of Ag plus in a saturated solution of silver phosphate? So how can we find the answer? Now I'm going to rewrite the reaction that we had in the beginning. So this was 3 and this was 1. Now keep in mind, X is the molar solubility for this substance, for Ag3PO4. So that's how much silver phosphate is dissolved in a solution, in a saturated solution. So what we need to do is convert it to this value. Notice that the ratio is 1 to 3. So we simply have to multiply our answer by 3. But if you want to show your work, here's what you could do. So start with what you have. 1.6 times 10 to the negative 5 moles of silver phosphate that's dissolved in a solution per liter. And now for every mole of Ag3PO4 that's dissolved, there's going to be 3 moles of Ag plus dissolved along with it. And so that's why we need to multiply by 3. So now we're going to have moles over liters for Ag plus. So the concentration of Ag plus in a saturated solution of silver phosphate is going to be 4.821 times 10 to the negative 5. And so that's the answer. The KSP value for lead phosphate is 1 times 10 to the negative 54. Calculate the molar solubility of Pb3PO42, lead 2 phosphate. So let's use the shortcut method. Let's write an equation that relates Ksp to X. So notice that the subscript for lead is 3. So it's going to be 3x to the third power. And for phosphate, it's 2. So it's going to be 2x raised to the second power. 3 to the third is 27. And 2 squared is 4. 27 times 4 is 108. So Ksp is equal to 108 times x to the fifth power. So let's replace Ksp with 1 times 10 to the negative 54. And so let's start by dividing both sides by 108. So it's going to be 9.26 times 10 to the negative 57. And that's equal to x raised to the fifth power. So we need to raise both sides to 1 over 5. So on the right side, this is going to equal x. On the left side, this is going to be 6.21 times 10 to the negative 12 moles per liter. And so that's the answer for part A. Now let's move on to part B. What is the concentration of phosphate in a saturated solution of lead 2 phosphate? So let's write the reaction first. So lead 2 phosphate is going to dissociate into the Pb plus 2 ion and also the phosphate ion. Now the coefficients, the subscripts are 3 and 2. So to balance it, we need to put a 3 here and a 2 in front of phosphate. So to calculate the concentration of phosphate, notice that it's twice the value of the amount of lead 3, the lead 2 phosphate dissolved in the solution. It's a 1 to 2 ratio. So if this represents the solubility of this substance, then the concentration of phosphate is simply going to be this number multiplied by 2. So it's going to be 6.21 times 10 to the negative 12 times 2. And so the phosphate concentration is 1.242 times 10 to the negative 11. And so that's it. So let's say if we need to calculate the lead 2 ion concentration, for example, notice that the molar ratio is 1 to 3. So it's going to be 3 times this number. So 6.21 times 10 to negative 12 multiplied by 3. So that's going to be 1.863 times 10 to the minus 11. So once you have the molar solubility, you can easily calculate the concentration of any product ion just by multiplying by the coefficient that you see here. Now let's move on to part C. Calculate the solubility of lead 3 phosphate in grams per liter. So we're going to start with this number. 6.21 times 10 to the minus 12 moles of lead 3 phosphate per liter. And all we need to do is convert moles into grams. So we need to calculate the molar mass of lead 2 phosphate. So there's 3 lead atoms, 2 phosphorus atoms, and 8 oxygen atoms. Now the molar mass of lead is 207.2. For phosphorus is 30.97, and for oxygen it's 8 times 16. So let's go ahead and plug in these numbers. So this is 811.54 grams per mole. So we're going to put 1 mole on the bottom. That's 1 mole of Pb3PO4, and it has a mass of 811.54 grams. So the units moles of lead phosphate will cancel. And so this will give us the solubility in grams per liter. So it's going to be 6.21 times 10 to the negative 12 multiplied by 811.54. And so the solubility is now 5.04 times 10 to the negative 9 grams per liter. So that's the answer. Now let's focus on solving common ion effect problems. So in this problem, we're given a KSP value for lead 2 fluoride. It's 4 times 10 to the negative 8. And our goal is to calculate the molar solubility of solid PbF2 in a solution of sodium fluoride. So first, let's write the dissolution reaction for lead fluoride. Lead fluoride will dissociate into lead ions and fluoride ions. Now we need to balance the equation. So this is going to be 1, and then we need a 2 in front of fluoride. Now let's make an ice table. So initially, the concentration of lead will be 0. The concentration of fluoride is 0.5 because the lead fluoride dissolves in a solution that already contains fluoride. Sodium fluoride is 0.5 moles per liter. Now, because the concentration of lead is 0, the reaction has to shift to the right. So therefore, Pb will increase by x, or basically we could say 1x, and fluoride will increase by 2x due to the 1 to 2 ratio that we see here. So in equilibrium, the concentration of Pb plus 2 is represented by x, and fluoride will be 0.5 plus 2x. So now let's write the KSB expression. So KSB is going to be products over reactants, and a reactant is a solid, so we cannot include that in the equilibrium expression. So it's just going to be products divided by no reactants in this example. Now we need to raise this to the second power. So that's the KSB expression for this reaction. Now the KSB is 4 times 10 to the negative 8. And the concentration of the lead 2 plus ion, we said it's X. And the concentration of fluoride is 0.5 plus 2x. Now notice that KSP is very small, 10 to the negative 8. That means X is going to be a very small value. So 0.5 plus 2 times a very small number is still going to be 0.5. So this 2x quantity is negligible. So now we have this expression, 4 times 10 to the negative 8 is equal to x multiplied by 0.5 squared. So to calculate the value of x, It's simply the KSP value, 4 times 10 to the negative 8, divided by 0.5 squared. And so x is equal to 1.6 times 10 to the minus 7. Now, x represents the concentration of the Pb plus 2 ion that's dissolved in the solution. And notice that the Pb plus 2 ion is in a 1-to-1 ratio with lead fluoride. So the amount of lead fluoride that's dissolved in the solution is equal to x in this example. So x represents the molar solubility. So that's the molar solubility of lead fluoride in a solution of sodium fluoride. So that's the answer to part A. Now let's focus on part B. What is the molar solubility of lead fluoride in a saturated solution of lead fluoride? So in this example, we want to calculate the molar solubility if it's not in a sodium fluoride solution. So it's just a solution that consists only of PbF2. So how is this problem going to be different than the last problem? What would you say? In this problem, the concentration of lead is 0, but fluoride will be 0 as well. We don't have a common ion in part B. So this is going to increase by 1x, this will increase by 2x. So the KSP expression, which is still going to be Pb plus 2 times the concentration of fluoride squared. In this case, lead is still x, but fluoride is simply 2x. There's no 0.5 in this example. But KSP is still going to be 4 times 10 to the minus 8. Now 2x squared is equal to 4x squared, and 4x squared times x is 4x cubed. So our goal is to calculate x, which represents the molar solubility. Now keep in mind, for the previous answer, it was 1.6 times 10 to the minus 7. Let's see what the new answer is going to be for part B. So first, what we need to do is divide both sides by 4. So 4 divided by 4 is 1. So on the left side, it's going to be 1 times 10 to the negative 8, and that's equal to x cubed. Now what we need to do now is take the cube root of both sides, or simply raise both sides to the 1/3 power. 3 times 1/3 is 1. The cube root of 1 times 10 to the negative 8, that's 2.15 times 10 to the minus 3. So this is the molar solubility in a solution of lead fluoride. So now let's focus on part C. What effect does the presence of a common ion, such as fluoride, have on the molar solubility of lead fluoride? So in part B, if we only had lead fluoride, notice that the solubility, the molar solubility, is 10 to the minus 3. But in the presence of a common ion, when we had the solution, the sodium fluoride solution, the molar solubility of PbF2 decreased greatly to 10 to the negative 7. So the presence of a common ion reduced the molar solubility of lead fluoride. And so anytime you have a common ion in a solution, the molar solubility of that substance will decrease. So now what we're going to do is we're going to go over potential energy diagrams. So let's start with this one. On the left, you have the reactants, and on the right, the products. At the top of this diagram, we have the transition state. also known as the activated complex. On the y-axis is the potential energy, and on the x-axis, this is the reaction coordinate. So notice that the products have less energy than the reactants. Whenever you see that, this reaction is considered to be an exothermic reaction. Exo means like outside. Exothermic means that heat is released out of the system into the surroundings. So whenever heat is released, the enthalpy of the reaction is negative. As you can see, the enthalpy is the difference between the potential energy of the products and the reactants. So it's products minus reactants. Because the products have less energy than the reactants, you're going to get a negative value. Now, what is the energy difference between the transition state and the reactants? What is that called? This is known as the forward activation energy. The activation energy is the energy that's needed to get the reaction started. Without that energy, the reaction will not work. So one way you can reach the activation energy is by increasing the temperature of the reaction, which will speed it up. Now, what is the energy difference between the transition state and the products? This is the activation energy, but for the reverse reaction. So if you need to go backwards, you got to go this way. Once you reach the transition state, that's when the reaction takes place. So you need enough energy to get to the transition state. Now, what's going to happen if we add a catalyst to this reaction? Now, we know that the purpose of a catalyst is to speed up a reaction. And enzymes are biological catalysts that speeds up reactions in living systems. Now, if we add a catalyst, we're going to have a new diagram that looks like this. As you can see, the activation energy is lower. Here, the activation energy is only this high, but before, it was significantly higher. So as you can see, adding the catalyst lowers the activation energy. And when you have a lower activation energy, the reaction will proceed faster. And so that's how a catalyst will speed up a reaction. It's by lowering the activation energy. Now, how can we draw the potential energy diagram for an endothermic reaction? If you wish to draw it for an endothermic reaction, you need to draw the products with a higher energy than the reactants. So the products have to be above the reactants. And now it's endothermic. So as you can see, delta H is going to be positive. Since delta H is products minus reactants, if you take a large number and subtract it by a small number, you're going to get a positive result. For example, 10 minus 4 is positive 6. In the left side, if you take a small number subtracted by a large number, you're going to get a negative result, like 3 minus 7 is negative 4. So because the products have more energy than the reactants, what we have is an endothermic reaction. So in this reaction, the system absorbs heat energy, it gains energy, and so the enthalpy of the reaction is positive. Now, it turns out that the enthalpy is really the difference between the activation energy of the forward reaction and reverse reaction. So let's put some numbers to this. So let's say this is at the products is at a value of 100, the reactants is at 300, and the transition state is at 600. So if we want to calculate, let's say, the forward activation energy, the forward activation energy is the difference between the energy of the transition state and the energy of the reactants. So in this case, that's going to be 600 minus 300. So the activation energy for the forward reaction is positive 300. Now, if we wish to calculate the reverse activation energy, it's the difference between the energy of the transition state and the energy of the products. So that's going to be 600 minus 100, which is positive 500. Now, if we wish to calculate the enthalpy of the reaction, it's the products minus the reactants. So the products have a value of 100, and the reactants is 300. So because the products are they're lower in energy, it's going to be negative 200. That's the enthalpy of the reaction. So notice that the enthalpy of the reaction is also the forward activation energy minus the reverse activation energy. The forward activation energy is positive 300. The reverse is negative 500. If we subtract these two, we're going to get the enthalpy of the reaction, which is negative 200, which is the same as this one. So you can remember these four equations. So that's the enthalpy. You can find it by subtracting the two activation energies, or you can take the energy of the products minus that of the reactants, and you can calculate the forward activation energy using those two. And here's the reverse. So four useful equations that you can get from the potential energy diagram. Now, what about a two-step reaction? How can we draw the potential energy diagram for that? So let's try it. So if you have a two-step reaction, there's going to be two transition states, TS1, TS2. The transition state is also known as the activated complex. So here's the reactants, and here's the product, and this is the intermediate, which is like, it's in the middle. So overall, is this reaction exothermic or endothermic? Notice that the products have less energy than the reactants. So therefore, the enthalpy of the reaction overall is negative. It's an exothermic reaction. Now, what about the enthalpy for the first step? Let's call it delta H1. Is it endo or exothermic? So for the first step, we're going from the reactant to the intermediate. Notice that the intermediate has more energy than the reactant, so we're going up. As you go up, that means the system has to gain energy, so therefore, delta H is positive. Now, as you go from the intermediates to the products, you have to go down in a potential energy diagram. So the enthalpy for the second reaction is negative. So for the first step, it's endothermic. The second step is exothermic, and overall, it's an exothermic reaction. Now, which step is the slow step or the rate determining step? Is it the first step or is it the second step? What would you say? Now, notice that the first step has a higher activation energy than the second step. So because the first step has a higher activation energy, because the transition state is higher than the second transition state, this is going to be the slow step because it's going to be a lot harder to go up this mountain than it is to go up this mountain. So this is going to be a slow step. It's going to take a longer time to get through TS1. TS2 is easy to pass through because it's not so high in energy. So the transition state that has the highest energy, it's going to be associated with the slow step. And so that's what you want to know for these types of diagrams. So here's an example problem for you. Draw a potential energy diagram that has three steps where the second step is rate determining and the overall reaction is endothermic. And let's say the first step is endothermic, the second step is exo, and the third step is endothermic. How can we draw such a potential energy diagram? Okay, so let's be careful with this. So overall, it's endothermic. And we said the first step is an endothermic step. So let's draw something like this. The second step is the rate determinant step, and also it's going to be exothermic. So it has to be very high if it's going to be the rate determinant step. If it's exothermic, it has to be lower than what it was previously. Now the third step is endothermic, and it's endothermic overall. So this has to be higher than the reactants. So this energy diagram meets the characteristics. This is TS1, TS2, since that's the highest. The second step is the slow step. And here we have the reactants and the products. Because the products is higher than the reactants, overall it's an endothermic reaction. Now intermediate 1 is higher than the reactants, so the first step is endothermic. Intermediate 2 is lower than intermediate 1, so the second step is exothermic. And the third step is endo because the products is higher than intermediate 2. And so that's how you can draw a potential energy diagram with 3 steps and the characteristics that we mentioned before. So that is it for this video. Thanks for watching, and I hope you have a better understanding of potential energy diagrams.
Hi guys, in today's video we're going to take a look at what is the Maxwell-Boltzmann curve, the Maxwell-Boltzmann curve looking at the influence of temperature and catalysts, an exam style question, and finally a summary.
So what is the Boltzmann curve? Well, the Boltzmann curve shows us the distribution of molecular energies in a gas at a constant temperature. So what we see is that some molecules move fast and have a high energy, as shown here. But some molecules also move slow and have a low energy, as shown here. But majority of the molecules we find have an average energy. So here we have our Boltzmann curve. On the x-axis we have the kinetic energy, and on the y-axis we have the number of particles with that specific kinetic energy. And there are a number of features of the curve that we're going to have a look at. First of all, the area under the curve is equal to the total number of molecules in the sample. Second, the curve starts at the origin. There are no molecules in the system with zero energy. And thirdly, only molecules with a greater energy than the activation energy can react. And we can mark the activation energy onto our graph where it applies. So now we've had a brief introduction to the Maxwell-Boltzmann curve. Let's have a look at it in specific relation to increasing the temperature of a reaction. Well, we know that at higher temperatures, the kinetic energy of the molecules increases. So what we'll see is that from our original curve, we have a slightly different curve. The peak moves to the right and it becomes a lower peak. So here, the curve labelled T2 is symbolising a curve at a higher temperature. Now it's important to notice that the area under the curve remains the same. The number of molecules in the system is exactly the same, but there are some slight differences. So what are they and what's happening? Well, the molecules are moving faster as they have more kinetic energy at a higher temperature. So we see a greater proportion of the molecules have an energy greater than the activation energy. So if we take a look at our graph, we can see that the activation energy is marked on here as EA. And we can see the proportion of molecules with energy greater than the activation energy at T1, the lower temperature, is shown in dark green, whereas the proportion of molecules with energy greater than the activation energy at T2 is shown as the area that's green and the area that's grey. So that's that total area altogether. We can see it increased. So this is because there are more successful collisions occur in a given length of time, and therefore the rate of reaction will increase. So now I've had a look at the curve in relation to increasing the temperature. Let's have a look at the curve in relation to the presence of a catalyst. Well, we know that the catalysts lower the activation energy of a reaction, and we can see that on our curve here. Here on the left, we have an activation energy with our catalyst, which occurs at a lower energy than the activation energy with no catalyst. So we know that our catalyst provides an alternative reaction route, a route that requires a lower activation energy. Now, they don't change the distribution of the molecular energies. You can see we haven't got a second curve forming. Instead, we just have this lower activation energy. So let's quickly recap what exactly is happening when we add the catalyst. Well, more molecules in the system have an energy in excess of the new lower activation energy provided by the catalyst and the alternative reaction pathway. So there are again more successful collisions in a given length of time. That's more collisions occur with energy in excess of the new lower activation energy, and therefore we see the rate of reaction increases. Shown below is a Boltzmann distribution of molecular energies. We can see that here. In part A, we're asked to label the diagram with the activation energy of the reaction with and without a catalyst. So firstly, if we suggest an activation energy without our catalyst, might be somewhere around here. Not many particles have an energy in excess of the activation energy. But with our catalyst, we know the activation energy is much lower and more particles have an energy in excess of the activation energy. We can see that with no catalyst, only the particles under the graph over here have enough energy to react with an energy in excess of our activation energy. But when we lower it with our catalyst, it's all these particles over here that can react. A nice and simple feature of our graph to get us that first mark. Moving on to part B, we're asked to explain how the addition of a catalyst increases the rate of reaction, making reference to the Boltzmann distribution of energies. So we know that our catalyst provides an alternative reaction pathway with a lower activation energy. We've just shown that on our graph. As a result, more particles have an energy in excess of this new lower activation energy, and therefore more successful collisions occur per unit of time. For our first mark, we've explained that the catalyst provides an alternative reaction pathway with a lower activation energy. Our second mark comes from explaining that more particles have an energy in excess of this new lower activation energy. And our third mark for explaining that therefore it's more successful collisions that occur per unit of time that increases the rate of our reaction. In part C, we're asked to add a curve to the diagram above, showing the effect of increasing the temperature on the Boltzmann distribution. Well, we know that when we increase the temperature, we increase the rate of reaction. And if we have a think about the curve we're going to draw, what we need is something with the same area, because it's the same number of particles, but with a lower peak. So let's take a look at how we're going to draw that curve and why. So it's going to have the same area because it's the same number of particles, but a lower peak and shifted to the right, something like this. This is indicating that more of our particles have a higher energy as we've increased the temperature. However, there is exactly the same number of particles. We've not increased that. So if we go ahead and label our curve, and if we take a look at the question, we can see that the question holds 2 marks. Each of these marks comes from a different feature of our graph. The first, for having a curve with roughly the same area, and the second for a lower peak, just as shown in our graph above. Moving on to part D, we're asked to explain how increasing the temperature increases the rate of reaction, again making reference to the Boltzmann distribution of energies. Well, we know that increasing the temperature shifts the curve to the right, as we showed above. If we take a look at our curve that we've drawn, we can see exactly what impact that has. So here we have our curve that we've just drawn showing the increased temperature. We can see that with our lower temperature, this many particles have energy in excess of the activation energy. However, with our increased temperature, more particles have an energy in excess of the activation energy, even if there's no catalyst used. So just extending that line, we can see that this many particles have an energy in excess of that activation energy if we increase the temperature. So let's go ahead and explain that in our answer. As a result of more of our particles having an energy in excess of the activation energy, more successful collisions occur per unit of time. This question holds 3 marks. The first comes from explaining that increasing the temperature shifts our curve to the right. The second for explaining that as a result, more particles have an energy in excess of the activation energy. And the third for summarising that and explaining that therefore more successful collisions occur per unit of time, increasing the rate of reaction.
Hey guys, I hope you're enjoying the video.
Welcome to our lecture online, and in this video we're going to look at the average, the mean, and the root mean square velocity as it applies to molecules. Now, looking at the average, the mean, and the root mean square of anything would be exactly the same as what I'm doing here. So even though we're talking about molecules, and I have an example of 9 molecules, with velocities in meters per second of 1 meter per second, 3 meters per second, 4 meters per second, and so forth. They're the 9 velocities. And we're supposed to find the average, the mean, and the RMS velocities of those molecules. And this could be anything, could be the masses, could be the momentums, doesn't matter. The method and technique would be exactly the same. So starting out with the average. V average is equal to the sum of all the velocities divided by the number of molecules that I have. So in this case, this would be equal to 1 plus 3 plus 4 plus 5 plus 6 plus 7 plus 9 plus 14 plus 20, all divided by the number that I have, and there's 9 molecules. Make sure, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then with a calculator, let's find out what that is equal to. So that would be 4, that's 8, that's 13, that's 19, that's 26, that's 35, that's 45, that's 49, that's 69 divided by 9. So 69 divided by 9 equals, and that would be a velocity of 7.67 meters per second. Of course, I left off the units there, but at least you could see the technique. So that would be the average velocity. The mean velocity, V mean, is simply equal to the middle one. So I pick one that has just as many velocities that are smaller than as there are larger than that quantity. Now, of course, I picked 9 molecules because that means that the one in the middle is the one, say 1, 2, 3, 4, that would be this one right here. So that would be the middle one. That means there's 4 molecules with smaller velocities and 4 molecules with larger velocities. And so therefore, in this case, the middle one means that it's equal to 6 meters per second. That would be the mean velocity. Now, why is the mean velocity smaller than the average velocities? Notice that there's 2 molecules that have a significantly larger velocity, and they throw off that average. That causes the average to skew to the right and gives you a larger average velocity, even though there are 1, 2, 3, 4, 5, 6 molecules that have a smaller velocity than that, and only 3 that have a larger velocity. That is still the average of the 9. The mean sometimes is a better representation of the typical velocity of a molecule, because this is much closer to the vast majority of molecules right there. All right, now the root mean square. VRMS is equal to the square root of the sum of the squares of the velocities. So the sum of the individual velocities squared, so I'll write V sub I, and maybe I should have written V sub I there. That means the individual velocities divided by the total. Here I'm going to take the sum of the individual velocities squared and then divided by the total number, and then take the square root of that. And of course, I made my radical way larger than I needed to. All right, let's do that now. We have 9 values. So this is equal to the square root of 1 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 9 squared plus 14 squared plus 20 squared, all divided by the total number that I have, which is 9. All right, so let's work that one out. So that would be 1 plus 9 plus 16 plus 25 plus 36 plus 49 plus, that looks like 81, plus 14 squared is 196, plus 400 equals, divide that by 9, equals, and then take the square root. And there we get the RMS velocity of 9.5 meters per second. That's interesting here. Notice how the RMS velocity is larger than the average and the mean. That is because the RMS velocity is really skewed by the fact that there's some large values. It gives extra importance to the molecules that have a large value because we squared that before we add it all together. And so this squared and this squared together is far larger than all the other ones squared together, and so therefore it pushes that RMS velocity to the right. Now, or to a larger value. Now, in the significance of that is when we have a whole slew of molecules and a small number of them have a very large velocity, that adds to the kinetic energy and that adds to the overall significance of these velocities within the whole. So since it adds to the kinetic energy, we need to account for it in a more, how should I say, more, it has more of an impact to the overall value, and so therefore this is a more representative of the representation of the velocities of molecules in a grouping. So RMS velocity is the important one, and you can see that it's typically larger than the mean or the average velocity. Welcome to our lecture online, and our next topic in thermodynamics is the Maxwell-Boltzmann distribution. This is the distribution of the velocities or speeds of molecules in any environment. For example, in the room or in a box, doesn't matter where it is. This is going to be the way the speed of the molecules are distributed. Now, here's the equation that describes this curve. And before you turn off the video and go, I am not going to understand that, hang on for just a moment. It's not really that bad. It is kind of a mean equation. And the people, Maxwell and Boltzmann, who devised this equation, they were very smart. It's an amazing feat of physics that they were able to figure out how that distribution can be mathematically mapped. But for our purpose, we just need to understand three different velocities among the velocities of the molecules in a box or in the room. One is called the RMS, or root mean squared velocity, and I put the equation up here already. We figured that out in a previous video, so if you want to go look at that video to figure out how to find the RMS velocity, there it is, and how to use it. That's the one we typically use for most of our calculations because the RMS velocity is really the representative velocity of all the molecules in the box. The effect that the molecules in a gas have on, let's say, the walls of the box, like in the amount of pressure they put on the walls of the box, that can be calculated when you assume that all the molecules have the RMS, or root mean squared velocity. So that's the important one. But there's two other important velocities. One is the average velocity, and the other one is the most probable velocity. The most probable velocity is the velocity that the most molecules have. Well, that's kind of misrepresentation. If you take a look, if you slice this up in small little slices like this, and then you look in each one of those slices and say, how many molecules move at that speed, you can go ahead and kind of count those up. And you can see that if you come to the slice that reaches up to the highest point of this curve, then you can realize that more molecules have this velocity than any other velocity, and that's therefore called the most probable velocity. And this is the way we figure out what that is equal to. So we take the equation right here, and we want to find the maximum point. And the technique to do that is to take the derivative of that equation and set it equal to 0. So before we take the derivative, I want you to look at a couple of things, and we're going to simplify the equation so it makes it a lot easier. First of all, take a look at this part of the exponent, e to the minus 1/2 mv squared divided by kt. Now, k is that gas constant divided by Avogadro's number, T is the temperature, and 1/2 mv squared, that's indeed the kinetic energy of the molecules. And here we have m divided by 2 pi kt to the 3/2 power times velocity squared. Now what that does is, the bigger the temperature, the lower this graph becomes, because T is the number in the denominator. Bigger T, it will lower the height of this curve. Secondly, because the T in here, if T goes up, it will stretch the curve off to the right. So at higher temperatures, it means that the distribution is more widely spread out, and it goes farther to the right, meaning they have higher velocities because of higher temperatures. So that's how you can interpret this curve.
Excuse me, sir. Nakamute ka, sir. Excuse me, sir.
v squared times the derivative of the exponent, so times minus 2c2v plus the second, which is e to the minus c2v squared, times the derivative of the first, which would be 2c1v. So times 2c1v. And now what we have to do with this is set this equal to 0 and solve for v. And that will be the v of the most probable velocity. Now, before we do that, we probably can simplify things a little bit by factoring out anything that's common.
Busan
I
lang
see
ni
an
kayo
e
sa
to the
akin,
minus
bubura man ni
c2v
siya. Pero
squared
importante
in
boss
both
na.
terms. I see a v squared here, and here I have a v times a v, which is a v squared. And actually, before I simplify it, maybe I should just multiply this out a little bit so you can, actually this is part of this term right here. So let me multiply everything out, and then you can see how this equation simplifies a little bit. So we have f prime of v is equal to, so multiply this times this, I'm going to end up with a minus 2c1c2. We have a v squared and a v, that means v cubed, times e to the minus c2v, e to the minus c2v squared. And then on the right side, we have plus 2c1v times e to the minus c2v squared. There we go. Now I think we can see that there's some common factors we can pull out. We can pull out this is equal to, we could pull out the 2, we could pull out the c1, so 2c1. We have a v and a v there, so times v times e to the minus c2v squared. This minus should be up here. There we go. And then what we have left, so here we pulled out, we have a c2, we have a minus, so we have a minus, we have a c2 left, we have a v squared left. And over here, we pulled out the 2, the c1, the v, and e, so we have just a plus 1 left. There we go. So there's our derivative. Now to find the highest v, so to find max v, or to find max function, I should say, max function of v, we set f prime of v equal to 0. That's a common technique in calculus where to find the highest or lowest point in a function, we simply take the derivative, set it equal to 0, and solve for the variable. So we're going to set this equal to 0. So 0 is equal to 2c1v e to the minus c2v squared times the quantity minus c2v squared plus 1. So for this to be equal to 0, notice that we have a product. We're multiplying this times this. So for this to be 0, either this must equal 0 or that must equal 0. Now, for this to equal 0, since we have v times this, v would have to be equal to 0. And yes, indeed, if we let v equal to 0, we have ourselves a minimum on the function. That's the lowest value the function can have. So that's not the answer we're looking for. We're looking for the maximum value. So we're going to concentrate on this portion right here. Let's set this equal to 0. All right, so 0 equals minus c2v squared plus 1. And so that means that c2v squared equals 1, or v squared is equal to 1 over c2, or finally we could say that v is equal to the square root of 1 over c2. Oh, okay, now let's go back and see what c2 was equal to. I made the substitution for this quantity right here. Everything but the v squared became c2. So I'm going to substitute c2 for 1/2 m over kt. So coming up here, we have v is equal to the square root of 1 divided by C2, and C2 would be 1/2 m divided by KT, like so. And of course, I'm dividing this by fraction, so I then flip that fraction over, so this is equal to the square root of 2KT over m. And then, of course, this is R divided by Avogadro's number, and this is the mass of a single molecule. So if I want to then multiply the top and the bottom by Avogadro's number, I can then say that V most probable is equal to the square root of 2RT divided by the molar mass. So instead of using the molecular mass, I use the molar mass. Instead of K, I use R. And here's the equation of the most probable velocity. Now compare that to what I had over here when I looked at the RMS velocity. It was equal to 3RT over m, and notice the most probable velocity is 2RT over m. So very much related, a little bit smaller, and therefore you can see that sure enough, the most probable velocity is this one right here. The RMS velocity is this one right here, and as we will see in the next video, the average velocity is somewhere between those two values, and we'll figure out what that is equal to. So if someone says, what is the most probable velocity? The velocity that has the most molecules traveling at that velocity, it is equal to the square root of 2RT over m. And thanks to Maxwell and Boltzmann, with coming up with this great equation, all we had to do is take the derivative, set it equal to 0, solve for v, and there's the velocity. And that's how you find the most probable velocity in the Maxwell-Boltzmann distribution of velocities of a gas.
Okay guys, so nahuman na to. Try to review na lang ato ang video. Very important ang Boltzmann, no? Kanunay siya mogawas ato ang designing sa reactor. Okay, so please open your microphone for the second attendance. Abarkis,
Present, sir.
Gasaldo. Gasaldo, no, wag tang.
Present siya, sir. Pero sige ka disconnect.
Brown out
Ulit
mo sa
ako,
ilang, sir.
mag-download na lang siya, no?
Oo, sir,
Ansita.
pero...
Sige, sige.
Present, sir.
Arong.
Present, sir.
Arios.
Present, sir.
Silvestre.
Present, sir.
Cañete.
Present, sir.
Caballero.
Present, sir.
Castañares.
Present, sir.
Pimente.
Present, sir.
Cuyos.
Present, sir.
Dakay. Dakay wala.
Present, sir.
Ana.
Nana.
Okay. Dinglasa.
Present, sir.
Dinopol.
Present, sir.
Durham.
Present, sir.
Yujan.
Present, sir.
Fabrique.
Present, sir. Present, sir.
Figueroa.
Present.
Gilina.
Present, sir.
Sarina.
Present, sir. Present.
Lacroma.
Present, sir.
Pando.
Present.
Luab.
Present, sir.
Oh. Lumibaw. So may status niya.
Present, sir. Lumibaw, present, sir.
Lumibaw. Okay. Mule.
Present, sir. Present,
Morok.
sir.
Yes.
Present, Morok, sir.
Okay. Vida.
Rita, present, sir.
Alice.
Present, sir.
Oh.
Present po, sir.
Pipito na ano?
Present, sir.
Perez.
Present, sir.
Andas. Daphne.
Present. Present, sir.
Okay. Report.
Present, Reponte, sir.
Okay. Ruben.
Present, sir.
Okay. Sanoy.
Present, Sanoy, sir.
Leo.
Present, sir. Sinilio.
Susun. Susun.
Present, sir.
Okay. Toledo. Toledo. None is Toledo.
Present na si Toledo, sir.
Okay. Vergara.
Present, sir.
Taon.
Present, sir.
Okay. So everybody's present. We're
Toledo,
good.
sir. Present, sorry.
Okay. Sige. And don't forget, we'll be posting our second assignment. And also very important, this coming Monday we will have our second quiz. No. By the way, apil na mo sa meeting adto kang Jade Dinopol because by next Friday doon na tayo ma-exempted no sa atong mga discussion no sa atong activities dia because we will have some activities sa school no. Okay? So kinsa man tong wala pa ma-aware, just ask Miss Jade no regarding that one. Okay? So if you have no more questions, you can log out now, guys, and God bless. Okay?
Thank you, sir.
Thank you, sir.
Okay, you're welcome.
Yes, sir.